Fermat pseudoprime. In number theory, the Fermat pseudoprimes make up the most important class of pseudoprimes that come from Fermat's little theorem. Definition and definition. Fermat's little theorem states that if P is prime and A is coprime to P, then AP11 is divisible by P. For an integer of 1, if a composite integer x divides x11, then x is called a Fermat pseudoprime to base A. Def. 3.32. In other words, a composite integer is a Fermat pseudoprime to base A if it successfully passes the Fermat primality test for the base A. The false statement that all numbers that pass the Fermat primality test for base 2 are prime is called the Chinese hypothesis. The smallest base -2 Fermat pseudoprime is 341. It is not a prime, since it equals 11*31, but it satisfies Fermat's little theorem 2340, 1 mod 341, and thus passes the Fermat primality test for the base 2. Pseudoprimes to base 2 are sometimes called Saris numbers, after P. F. Saris, who discovered that 341 has this property, Poulet numbers after P. Poulet, who made a table of such numbers or formations sequence of 1567 in the OEs. A Fermat pseudoprime is often called a pseudoprime, with the modifier Fermat being understood. An integer x that is a Fermat pseudoprime for all values of a that are coprime to x is called a Carmichael number. Def. 3.34. Properties. Distribution. There are infinitely many pseudoprimes to any given base of 1. In 1904, Sapala showed how to produce an infinite number of pseudoprimes base of 1. Let P be a prime that does not divide at 1. Let A equals AP1/A1 and let B equals AP+1/A+1. Then N equals AB is composite and is a pseudoprime to base A. For example, if A equals 2 and P equals 5, then A equals 31, B equals 11, and N equals 341 is a pseudoprime to base 2. In fact, there are infinitely many strong pseudoprimes to any base greater than 1. See theorem 1 of, and infinitely many Carmichael numbers, but they are comparatively rare. There are 3 pseudoprimes to base 2 below 1,000, 245 below 1 million, and 21,853 less than 25*109. There are 4,842 strong pseudoprimes base 2 and 2163 Carmichael numbers below this limit. See table 1 of. Starting at 17*257, the product of consecutive Fermat numbers is a base -2 pseudoprime, and so are all Fermat composite and Mersenne composite. Factorizations. The factorizations of the 60 Poulet numbers up to 60,787, including 13 Carmichael numbers in bold, are in the following table. Sequence of 1567 in the OEs. A Poulet number all of whose divisors D divide 2 is called a super Poulet number. There are infinitely many Poulet numbers which are not super Poulet numbers. Smallest Fermat pseudoprimes. The smallest pseudoprime for each base equals 200 is given in the following table. The colors mark the number of prime factors. Unlike in the definition at the start of the article, pseudoprimes below are excluded in the table. For that to allow pseudoprimes below A, see OEs Animetti 1086. Sequence S7535 in the OEs. List of Fermat pseudoprimes in fixed base N. For more information, base 31 to 100 see OEs at 20,159 to OEs at 20,228, and for all bases up to 150, see Table of Fermat pseudoprimes text in German. This page does not define N is a pseudoprime to a base congruent to 1 or -1 mod. Which bases B make in a Fermat pseudoprime? Weak pseudoprimes, Euler-Jacobi pseudoprimes. Another approach is to use more refined notions of pseudoprimality, e.g. strong pseudoprimes or Euler-Jacobi pseudoprimes for which there are no analogues of Carmichael numbers. This leads to probabilistic algorithms such as the Solovay-Strassen primality test, the Bailey-PSW primality test, and the Miller-Rabin primality test, which produce what are known as industrial-grade primes. Industrial-grade primes are integers for which primality has not been certified, i.e. rigorously proven, but have undergone a test such as the Miller-Rabin test, which has non-zero, but arbitrarily low, probability of failure. Applications. The rarity of such pseudoprimes has important practical implications. For example, public key cryptography algorithms, such as RSA, require the ability to quickly find large primes. The usual algorithm to generate prime numbers is to generate random odd numbers and test them for primality. However, deterministic primality tests are slow. If the user is willing to tolerate an arbitrarily small chance that the number found is not a prime number,